before I start, I would like to introduce myself. My name is Andreea Bodnari. I have just graduated with my PhD from MIT. I was working on natural language processing over there. I'm currently the chief data scientist at Movable Ink, which is a startup just next door. And I would like to start with a little bit of a grander vision. And I would like to bring you guys back to 2010 when the Haitian earthquake happened. And what happened over there was a catastrophe. The local government was not equipped to handle the situation, and most of the help came from international teams. Those rescue teams did not speak the local language, and it was very hard for them to communicate with the locals to understand where they had to provide help, where the rest of the family members were located, and what were their injuries. So you can see why it's so important for us to speak language understanding and actually be able to handle the numerous languages that exist today on this world. And the first question that might come to your mind is, how many languages? There are around 7,000 languages that we speak today to a various degree. And those languages can be categorized based on how many people speak them. And the largest category of languages contains around 4,000 languages. We call those small languages because they have a small vocabulary and also a rather limited range of expressivity. Those small languages are spoken by only 0.2% of the world's population. The very next category contains 3,000 languages, and those are spoken by 20% of the world's population. Those 3,000 languages are so-called medium-sized languages. And the last category, spoken by 80% of the world's population, contains only 80. And you might say, okay, you have a problem to solve. Why don't you just focus on those 83 languages, right? If you solve that problem, you make 80% of the world's population happy. But we've been trying, and for decades, we've put research into trying to understand those languages, and the best we could do is tackle around half of those languages. And roughly speaking, we can computationally model around 40 languages. And the problem we have is that language is the key to communication, but we are yet to successfully simulate it. And the current approaches we have taken so far resemble more or less a language puzzle, where you'd start with small pieces and you try to build on top of them in order to gain an understanding of what language actually means and what it tries to convey. In trying to understand this puzzle, we start with the simple things, with words and sentences. And once we've identified the words and the sentences, we move on. And we know that some languages have millions of words, and we want to categorize into something that we call word categories. Those are actually parts of speech, and some of those parts of speech are things like nouns, verbs, adverbs, adjectives. So you have those two things together, and the next thing you try to do with a computational system is to understand the relations that exist between the words. Those are called syntactic relations, and they're concerned with things like, is this noun actually dependent on the verb, or is this noun dependent on another verb? And you try to build structural dependencies that handle the grammatical arrangement of a sentence. And once those three pieces are in, you move further along and you focus on semantics. And semantics is really important because it's actually going to help you understand the meaning of the language. The meaning of a language is a very complex thing to handle because depending on the context I'm saying something, I might mean a totally different thing. And this is what pragmatics tries to figure out. So for example, if I am to say, I hate you, right? Does it actually mean I hate you? If I'm saying it with a smile on my face, probably not. So pragmatics tries to understand, given the context, what is it that the speaker actually tries to convey. And once those puzzle pieces are put together, we can say that we've understood the specific language and we can build computational models to simulate it. But the big picture doesn't look that great. For English, we might have this puzzle and we know how to simulate this language. By looking at other languages like German or Korean, the puzzle looks incomplete or barely touched. And languages like English, we called resource-rich because we have linguistic resources for them, while languages like Korean are resource-poor. Now, what I mean by resources, those are language models, linguistic knowledge, and annotations. For those of you who do not have a linguistic background, Annotations are our way to evaluate how well a computational model performs. And annotations are actually built by a set of people. We assign this task of annotating documents for a specific linguistic phenomenon, and then we build a system, a computational system that tackles the linguistic phenomenon, and then we evaluate against what the expert in the field, the humans, said to be the correct answer. Cool. So there's a lot of variability in terms of how well we understand language. And we've seen that we've only tackled a small portion of the languages that exist in the world. The question is how to scale. How can we take the knowledge we currently have and just expand it to the remaining 98% of the world's languages? The intuition that we got came from looking at the big picture. And the big picture told us that languages have a common underlying structure. This is something that linguists, after maybe a couple of years of debates, have agreed upon. And we know that languages are structured into families, and we call those language families. So for example, we have Germanic languages like English, German, Dutch. We have Romance languages like Italian, French, Romanian. We have Altaic languages. Those are languages like Turkic languages, Mongolic languages, Koreanic languages. And we also have languages like Dravidian languages, mostly spoken in South Asia. And some of the Dravidian languages are Tamil, Telugu, Kannada. And what we've noticed is that within the language families and across the language families, there was a variability in terms of how well we understood each language. So our goal was to take a specific target language for which we didn't know how to simulate it computationally, and then just borrow knowledge from languages from the same language family or from more distant language families on which we have that computational knowledge on. And in that way, we can kind of put together a computational system that's going to provide us a good enough solution for the target language on which previously we did not have this knowledge on. And as you can see over here, the puzzle that we've put together for the target language doesn't look that perfect. The pieces don't fit together perfectly. And it's not because my Photoshop skills are bad. It's because you're not going to have a perfect solution. The solution you're going to come up with is going to be good enough, but not the ideal. You will be able, though, to polish it further and customize to the target language, but you will have at least a starting point. Cool. And the languages from which we borrow this linguistic knowledge, we call them source languages. The language on which we apply the knowledge are called target languages. And what we're going to see and what I'm going to discuss on further is how to develop language models for resource-poor languages using linguistic knowledge from resource-rich languages. And I'm going to focus on two particular language models, the one that tackles syntactic relations and the one that tackles semantics. Okay, now before I move on and I talk about syntactic relations, do you guys have any questions? Okay. Now, syntactic relations. To give you an example of what syntactic relations are and how we try to model them, if we just look at the sentence that's up there on the slide, and let's focus on the latter part of the sentence. We are yet to successfully simulate it. When you read the sentence, your brain kind of identifies that there's a specific action that's being referred to in the sentence, and this action is conveyed through the verb are. And as you read the sentence, you start building relations between the words in the sentence. So for example, you identify the fact that we is the subject of the sentence, and the subject depends on the verb are, that yet is the adverb, and again, it depends on the verb are, and so on and so forth. You kind of build structural dependencies between the words in the sentence. And what we want to do is to simulate this kind of a process through a computational model. And this computational model we want to build is called a parser. This parser takes as input a sentence, and it outputs the dependency parse for the specific sentence. The problem we are having in the parsing world is that we do not have parsing systems for resource-poor languages. And the approach we have taken is to develop such multilingual parsing systems that begin by identifying source languages that are similar to a specific target language I want to focus on, and then we selectively apply knowledge from the source languages to the target language. The general approach we're taking is we start with a set of source languages, the languages that we call resource rich, because we have linguistic knowledge on. And we figure out a way to transfer linguistic knowledge that's applicable to our target language and use this linguistic knowledge from the source languages in order to train a parsing system that is then used to generate dependency annotations for the target language. And the challenge at this point was how can we select this knowledge from the source languages, right? What would be a good approach? And the first intuition we came with is maybe if we just focus on the languages that are from the same language family, right? We already know, according to linguists, that languages from the same language family have an underlying common structure. They have a set of shared properties. So maybe if we just bring knowledge from those source languages that are from the same language family with the target language, we're going to bring the correct knowledge and we're going to have a good enough parsing system for our target language. And this worked great for some of the languages, specifically for languages for which resources were available within this language family. But if you look at African languages, if you look at Dravidian languages, we just do not have knowledge of their language family. And we had to figure out a way to bring the appropriate knowledge without making this assumption that we have to bring it via the path of the language family. So the next scenario we looked at for bringing this knowledge on for the target language was by assigning a set of weights to each of the source language. And this specific weight would tell us how similar the target language was compared to how similar the source language was compared to our target language. Specifically, what that means is how much typological similarity is between those languages. And the intuition is that if the languages are typologically similar, then I should be able to bring the correct kind of linguistic knowledge and train a good enough parser for my target language. And of course, these weights are between 0 and 1, and the higher the weight, the more linguistic knowledge we were able to bring from the specific source language. The system performed better than the language family voting system, where we were bringing knowledge via the language family path, in terms that we had less variability across the languages on which we were evaluating on. But we've noticed something interesting. We've noticed that, for example, in English, I might have a sentence that has a structure that resembles most the structure of sentences in German. And I might have another sentence in English that resembles the structure of sentences in French. So even within a language, there was variability in terms of how the structure of sentences looked like. And that made us think that maybe by assigning weights at the language level is not the best granular level we should focus on. And maybe we should try to weight how relevant the source languages are towards the target language at the sentence level. So what we did, actually, is we took each sentence within the target language, and we assigned a weight for each of the source language that would tell relevant the source language was compared to the specific target sentence we were looking at. And then we were assigning weights for each sentence and running experiment. We were taking a new sentence, assigning weights, running the experiment. This specific experimental setting got the best results. And those results were good across all of the languages, across all of the language families. They performed better than the language level voting system. And we've also managed to outperform one of state-of-the-art system. The state-of-the-art system at the moment, this thesis was being written. Now, bragging about how well we did, I think you guys want to see some data. And in the interest of time, I'm going to focus on the experimental results we've obtained for the sentence level voting system only. The system where we basically assigned weights for the source language, and those weights were telling what was the syntactic similarity between the source language and each sentence within the target language. We evaluated our system across 16 languages from 9 language families. Those languages were annotated and prepared during the 2006 and 2007 Connell Challenge. And in this graph that just popped up on, in this graph you can see the sentence level system results displayed with the red color and the language level results displayed with the green color. And you can see that by assigning weights at the sentence level, we've managed to outperform across all of the languages the system that was assigning weights at the language level. And specifically, if we focus on some of the languages like Bulgarian, Slovene, Arabic, Hungarian, Japanese, languages that had a very intricate sentence structure, we were able to obtain quite a significant improvement compared to when we were assigning the weights at the language level. And that is because we were able to account for this variability within the sentence structure of the target language. Now, looking at how it performed compared to the state of the art, we've evaluated our system by looking at the parsing system of Nassim et al. The system was published in 2010, if I'm not mistaken, and was having a similar approach to parsing languages, borrowing knowledge from a set of source languages, just that they were not looking at this sentence level granularity. And compared to the state of the art, we've managed to outperform it on 10 out of 14 languages. For 4 of those languages, for Basque, Chinese, Japanese, and Turkish, we were not able to obtain as good results. But for the remaining 10 languages, we've managed to outperform and perform better than the language level voting system. And what we've concluded is that sentence level parsers are the way to go, because they were able to outperform the language level parsers, and overall, they outperformed the state of the art system. Do you guys have any questions up to this point? So syntactic, the question is, how did we judge syntactic similarity? Syntactic similarity was used when we were comparing how similar a specific sentence was to a target language. And that was computed by looking at the Levenshtein distance between the part of speech sequences of the target sentence compared to all of the sentences within the source language. Yes. So the question is, how did we account for pragmatics? We do not. It's very hard to account for pragmatics, mainly because you have to have this contextual information, and there was no way for us to have that. So for the purpose of this research, pragmatics was not considered. Yes? Mhm. Um, so we tried to be as unrestrictive as possible when modeling the system. The system was selecting automatically from where to bring the knowledge on, so we did not want to interfere with, we know this variability is in this specific area, just focus on this area and bring the knowledge from the specific language. So we did not input any linguistic constraints or any external knowledge. It was all learned kind of agnostic of what was going on in terms of variability. Okay, yeah? Would you mind repeating that question? Oh, so yeah, the question is how we would represent the input versus the output and what was that we were trying to evaluate on. The input was a sentence, like sentence level parsers outperform language level parsers. That was a sentence that we were taking as input. And what we wanted to take as output was 101 directed dependencies for each of the word within the sentence. So we wanted to know for word number 1, who it depends to. And depending to means that there was some sort of a grammatical relationship between those words. Uh, those are the categories of the words. What we were looking at was what was the relationship between the parts of speech within the sentence. So the part of speech would be this is the noun. The syntactic dependency would be this is the subject of the sentence, and it depends on the verb. Okay. Now I'm going to move on and talk about something that was a little bit harder for us to achieve in terms of good performance, and that was semantics. And semantics is really hard to tackle and solve computationally because it's so ambiguous. And there's so many ways in which you can express things, and even us, humans, the expert in the field, have a hard time figuring out what's the right interpretation of a specific sentence. And one way that you can account for the fact that the system is able to understand the semantics of a document or of a text is by looking at, does your system understand what are the concepts that are being conveyed within this document? And is your system able to build relationships within those concepts? So looking at an example, the one that just popped up on the deck, Audi is an automaker that makes luxury cars and SUVs. The company is based in Germany. One way you can evaluate whether your system knows what you're talking about is by looking at, does your system recognize the fact that you're talking about Audi, which is a company that makes luxury cars, and whether it can also identify the fact that there's another concept being mentioned, and specifically Germany. And the way we do this is by running a computational system through the document we're interested in. And in the first step, we would identify the concepts that exist over there. In this case, we would identify the fact that audience concepts that the text is referring to. And you would also identify the fact that Germany is being mentioned. And the second thing you would do is you identify the fact that there's a relationship present, and that relationship is an identity relationship. This specific linguistic phenomenon, it's called coreference resolution. And what we wanted to tackle in terms of semantics was this problem of coreference resolution. Of course, when you do coreference resolution, you look at mentions of concepts, and Audi and the company are considered the same concept, and the individual phrases Audi and the company are mentions of a concept. And when you run a computational system, you can run it in a sequential manner. But you can also run it in an end-to-end manner, where you just run through your text that you're interested in, and you identify the presence of mentions and the presence of a relationship between the mentions within the first step. And the problem we wanted to tackle in terms of coreference resolution was that there was no multilingual system that could perform end-to-end coreference resolution for resource-poor languages. And the solution we came up with was actually designing such a system, designing a system that was able to learn the mentions and the presence of a coreference relation between those mentions by using the syntactic knowledge that was brought from source languages, by using very limited linguistic knowledge on the target language. And that helped us design a language-independent system. And this linguistic knowledge that we induced into the system was in the form of linguistic constraints that were universal across languages. And what that means is that we could take our system, consider it an out-of-the-box system, and apply it to whatever resource-poor language we have, and still understand to a certain degree what was the semantic, what were the coreference relations for that specific language. To implement this, we took a probabilistic graphical model approach. Basically, we worked with a factorial hidden Markov model that contained 2 layers and 2 observation states. The first layer in our hidden Markov model was trying to target dimensions within a text. And basically how this factorial Markov model works is it takes a sentence, and for each word within the sentence, it considers it to be a Markovian step. And at each word, it tries to predict with the first layer whether that is the beginning of a mention, the inside of a mention, or if it's not a mention at all. So for example, if I have New York City, my hidden Markov model is going to run through New, and then through York, and then through City. And when it's at New, it's going to predict this is the beginning of a mention. When it's at York, it's going to predict this is the inside of a mention. And when it's a city, it's going to predict this is the inside again. And everything else outside of a mention is considered to be none. And once the system identifies that at the specific word step there is a mention, It also tries to predict whether there's a coreference relation that ties that specific mention to other mentions it has seen in the past. And in order to know what it has seen in the past, it has to maintain a visibility over what the past looked like. And the regular implementation of a hidden Markov model only gives you visibility over the previous time step, and you can predict what's going to happen at one step in the future. In order to accommodate for a larger history stack, we've enhanced this model with a mention queue. And what we were storing in this queue were the most recent K mentions. And every time we had a new word, we had to predict the coreference relation for. We would run through this queue of mentions. We will compute a similarity score between the two. And then we would predict whether there exists a coreference relation or not. And we would predict to which mention within this queue the coreference relation refers to. In terms of the observations, we chose to work with two observation states. The first one was the universal part of speech, and this is actually the word category that was assigned for the specific word we were working with. And the second observation state was the universal dependency label. So basically the dependency relations that were generated by our previous language model. The reason why we decided to work with two observation states and we've excluded modeling around words is because we wanted the system to be unlexicalized. That means that the system had to be language agnostic. We would be able to apply it to whichever resource pool language we had to tackle down. And language agnostic is good, but you still have to put in some linguistic knowledge. And this linguistic knowledge we implemented in the forms of linguistic constraints. Those constraints were mostly focused at what was the dependency between the two hidden layers of the Markovian model. And one such constraint basically was telling us that if I'm working with New York City and I'm in the middle at the word York, and my model has predicted that there exists a coreference resolution at a specific word, then coreference resolution should have been predicted for the word new as well, because coreference relations have to be carried throughout the entire mention. Another such constraint was that coreference cannot exist without a mention. And you can imagine why it cannot exist. And there were a handful of other constraints, linguistic constraints, that we modeled into this system. Now, looking at the experimental setup, what we did is we took the model and we trained it over a set of source languages, and then we evaluated on the target language to see how well we were able to translate this linguistic knowledge from the source languages to the target language. And basically, it was kind of a hybrid scenario because we didn't have linguistic knowledge available in the target language, and we were bringing knowledge from the source languages. And to evaluate the system, we looked at, and to put things into perspective, basically, we had to look at how the state-of-the-art systems were performing. We compared our system against the two best state-of-the-art systems, the Sucre and the Ubu systems. They were both supervised. That means that they were using linguistic knowledge that was available for the target language. And they were lexicalized. That means that they were modeling around the words of the specific target language. And in comparison to those, our system was supervised, but was supervised on the source languages, and it was not lexicalized. It was using the part of speech and dependency information in order to predict semantic knowledge. Now, the results are going to be presented separately for the mention recognition and for the coreference resolution tasks, because those are evaluated using different metrics. For mention recognition, we've looked at 4 languages, Catalan, Spanish, English, and Dutch. Compared to the 16 other languages we were working for syntactic relations, Coreference Resolution had a much smaller number of languages because annotations have not been developed for a lot of languages. It's just time-consuming, and we did not have the time, the human resources to develop annotations. Looking at the results, the system we have developed is presented in blue, and the state-of-the-art systems are presented in a red shade. What we've noticed is that for the Romance languages, for Catalan and Spanish, our system managed to perform better than the second state-of-the-art system. but they didn't manage to outperform the top best system. And you have to keep in mind that these systems were both trained on the target language. Now, for English, of course, a language where most of the linguistic resources reside, we were not able to compete with those systems that were trained on the target language and that also had linguistic knowledge available. But if we look at Dutch, a language where we kind of were evaluated on the same par with the state-of-the-art systems, because linguistic resources are not as rich for Dutch, we managed to outperform both the top state-of-the-art system and the second best state-of-the-art systems. So given a resource-poor language, our system managed to outperform the state-of-the-art systems. Looking at Coreference Resolution, a similar conclusion applied. We were able to outperform the second best, this time on Catalan and English. And then we were able to perform equally to the top state-of-the-art system. And you can see that the state-of-the-art system has a little advantage over us, but that was not a statistically significant advantage. So even for Coreference Resolution, we were able to outperform on languages that were actually resource poor. Now, the conclusion of this research is threefold, and there are three takeaway messages I would like you guys to live with. The first one is regarding joint learning of linguistic components, right? Modeling, named entity recognition, and coreference resolution together. And what we've learned is that this joint learning of linguistic components benefits computational models in resource-poor and multilingual settings. The second takeaway message is regarding cross-language knowledge transfer. Basically, looking at granular syntactic information that you assimilate from source languages, you can take this knowledge and apply it to resource-poor languages and actually build good systems that manage to tackle the puzzle for resource-poor languages. And the third conclusion is more visionary, and that is that you have to embrace the variation. You cannot expect that you're going to have linguistic resources or insights, but you can kind of learn how to model this unknown and still scale language understanding to the remaining 98% of the languages. And this is what we've tried to do. This is just the beginning. We've learned that we can walk the walk and that we can get there in terms of generating good enough systems for languages for which before we didn't know how to crack the code. And there's still a lot of research to go into it, but we have some sort of assurance that we're walking on the right direction. And last but not least, I would like to acknowledge my wonderful advisors and committee members. This research was made possible due to three funding sources, the SHARP project, the Chateaubriand Fellowship, and I2B2. And also, I would like to thank my amazing collaborators. If you have any questions, I'd be more than happy to take them now. Yes, in the back. Basically, how long it took for system to get trained. So it depends. For syntactic parsing, it was easier because the problem was not as complex. For understanding coreference resolution, this was a little harder problem, but in general, our system depended on how many linguistic constraints we're imposing on it and how much data I had to chunk through in terms of training data. But the system was able to finish within a couple of minutes. So it was scalable in terms of time complexity as well, not just scalable in terms of going to other languages. Yep. What do you mean by graphs? Uh-huh. So I'm not sure whether that would be applicable in this case. The documents we were working with were newswire documents, and there was not necessarily a speaker. It was mostly a writing style. And then there was a lot of variation across languages. The documents we were working with were not parallel documents, right? And you could not account for the fact that this language performs better because there's variation in terms how the person expresses himself or herself, rather than it's a totally different writing style or totally different source from where the knowledge is taken. Or maybe I didn't get your question. So these are not translations. What we were actually doing is just trying to consider all languages to be a bag of knowledge and try to extract from this bag of knowledge the knowledge that was representative for the target language we were looking at. So you could build translation models, but this is not what we built. You could expand this work and actually build translation models, but we were not there in terms of with the approach we've taken. Yep. Mhm. Yep. So the first question was whether I have a demo around this work and visualization for what I've discussed about. I have visualizations. They're not ready. They're not within this presentation. The demo is not available. We did not build that. It was a 4-year-long research project, and that's a bit shorter than the 5-year span that you have for a PhD. So I did not have as much time and resources to put into presenting this as well as it should have been. Regarding the second question, data is available. Some of the data we've used is actually the Connell data. We've also developed our own corpus, which is available on my MIT webpage. So I can point you to it afterwards if you want to take a look at the data. And the code is in the works. We're trying to make it available for the public. Yeah, parts of it are in my thesis, so I could share the thesis work if you're interested in. Yeah. Uh, so the question is around what was the level of, at what point you decide this is a resource poor language and you can actually build a model for. And I think you're hinting at the fact that we had resources even for the resource poor languages, but we didn't, right? So this approach should work for any language that you maybe just come across in a Hebrew text and you don't know how to process it and you don't know that's Hebrew. And you could just go ahead and apply the system to it and understand what are the syntactic relations and understand what are the semantics for the specific document. So we make no assumptions about what resources are available for the resource poor languages. That's a good question. Yeah? So would you mind repeating the question? Would, uh-huh. So some of the challenges we had to face were when the set of source languages was not as relevant towards the target language we had to work with. And we saw that challenge very visibly when we didn't outperform the state of the art on those 4 languages, because those languages were very structurally different, and they did not have any like much similarity to what was in the set of source languages. And for those languages, it might have happened that maybe there's nothing similar to them, right? We were not able to reach that conclusion because we did not have an even larger set of source languages to work with. And the languages, the source languages we were working with were kind of connected in terms of the language families they were coming from. So it was either 4 languages from the same language family or only one language from a specific language family. There was not much, you didn't have many siblings within the language families. Mhm. So that was a problem, and partially it was addressed by the fact that we allowed sentences to be modeled from different set of languages, depending on is there projectivity or non-projectivity. So in a sense, that addressed this problem of different structures and different types of dependencies across languages. I don't think I got a did you get by any chance? Yeah, that might help.
I'm curious if you looked at how multi-word expressions
Oh, okay.
of those ways were represented in the different language families. You know, you alluded to
Yep.
the New York City
Mhm.
example and co-reference resolution. I'm just curious if you looked at how multi-word expressions were represented in the different families.
So the question is how do multi-word expressions play in the world of coreference resolution? Because to do coreference resolution, you have to first identify these mentions, and sometimes the mentions span multiple words. In languages like English, you have a lot of such expressions that span multiple words. In languages like German, you have those multiple words concatenated together, and this no longer becomes a problem. So that was definitely a challenge. That's why most of the times when we do evaluation, we look at a partial evaluation schema, where even though you've missed a word of your concept, you still grant the right credit to your system. And this is the way we kind of tackled this challenge by granting the right credit, even though there was one missing word, maybe the beginning or maybe the end of it. And if we had, for example, if we had to predict on English and we were training on French, then we would obtain better accuracy on English compared to when we were training just in on German and had to apply to English, because German would tell us that most of the mentions had to be only one word mentions. So those are still challenges that have to be addressed, and we don't have a perfect solution for them. Very good question. Yeah?
Are the mentions discrete or are they more probabilistic where
They're discrete.
so it's either a mention or it's not?
Well, when annotators annotate the documents, they might have a probabilistic mention criteria, right? Because some of them might say this mention is 4 words, and some other might say this mention is 5 words. But we give them a guideline, right? And we annotate against the guideline, and then we have an external person who comes in and decides on what's the right number of words to include. And once we decide that that's the right number of words to include, that's what we expect of our system to predict. So, but there is variability with language in general. There's a lot of ambiguity, and there's a lot of ways you could interpret what it's supposed to be predicted and what the system is predicting. And what we found actually is that for some of the languages, our system was predicting the correct mentions, just that the annotations were incorrect. But you evaluate against the annotations, and you have to assume that's the gold standard. So it depends what the annotation guideline specifies. Because those should be things clarified in annotation guideline, and then when you train, your system learns that it's supposed to include or exclude processing. And we did not work with overlapping mentions. They were supposed to be one-off, yeah. Yeah?
Where is the model performance? Because it's for semantics. What level? It's like a 10 years ago, 12. It will function at that level. How well does it perform? Can you hear me?
Yeah, would you mind repeating? Because now I can hear you.
How well is the model perform? Particularly in terms of semantics. It's like able to function at a 10 years old child, or it's I mean, how well does it perform?
You mean how good is the performance of the model?
How well? How accurate?
Yeah, how accurate?
Particularly in semantics-wise. Semantics-wise. Yeah.
Semantics-wise. So the performance of the model, as shown in the previous slides, varies from the mention recognition task and the coreference resolution task. On mention recognition, we're able to do better, around 60%, 70% for some of the languages. Coreference resolution, the best performance was around 40%. Coreference resolution, on the other hand, is evaluated more stringently because your model will identify mentions, but if those mentions are not in a specific relation, there's a different way to weight how you consider the identification of mentions that are in a relation or not. But overall, going with the current metrics that are considered gold standard, we were obtaining 40%. And those are the Mach, B cubed, and CAF metrics. Yep. For which part? For syntactic relation, there's a lot of approaches. Syntactic relation has well been investigated. Coreference resolution is not, I mean, there's a lot of work in coreference resolution, but not a lot of work where there was done joint learning over the two different tasks that are required. So for coreference resolution, this was one of the first approaches, and also the first approach that was working with multilingual knowledge. We can talk more offline if you'd like.